Rigid objects do not exist. They are an approximation. If you compress too hard an object, you will deform it. You will modify its dimensions. In many situations, it is a great approximation to consider solid objects as non-deformable, as objects that maintain the dimensions and the shape constant. But this is not always the case. So far, we have considered forces that affect the motion of objects. Now we will consider forces that can deform objects. And we have already seen an example with the spring. The spring is an object that, under certain external stress, it stretches or compresses. It experiences a strain. Hooke's law says that the force applied, the stress in this case, is equal to the constant times the elongation, which is the strain. The elastic constant of the spring is what we call the modulus of elasticity. For relatively small stress, the spring recovers its original dimensions and shape. Then the spring is in the elastic regime. This is a linear regime. In this regime, once the stress is released, the object returns to its original state, to its original size and shape. If the force applied is even larger than a certain threshold, the elastic limit, the called yield strength, then the spring does not recover its original state and gets permanently deformed. We are not in the elastic regime anymore, and we are in the plastic regime. We would be in the regime of permanent deformation. For extreme stress, we can reach the fracture point and break the spring, for example. Hooke's law is just a particular case of the following expression. Stress, defined as force per unit area, equal to Young's modulus y times the strain, defined as the unit deformation delta L over L. We can use this expression not just for elastic spring, but any object under tensile or compressive stress. Think of a beam on a building. Think of your bones. Think of a rubber band or a rail as a train passes by. It can also happen that the stress is a shearing stress. We also define the stress in that case as the force per unit area. But in this case, the direction of the force is perpendicular to that area instead of parallel or anti-parallel to it. Again, the strain is the ratio between the deformation delta x over the length of the object L. But there is more. Think of a scuba diver that goes deep down into the ocean. That person experiences forces coming from all directions that want to compress her. Here, too, we define the stress as the force per unit area, also known as the pressure, which is equal to a constant, the bulk modulus, times the ratio between the change in volume, delta V, over the volume, V. Because the stress has units of pressure, that is pascals in the metric system, and the strain is unitless. This means that Young's shear and bulk modulus, all three, have units of pressure. These are some values of Young's shear and bulk modulus for some common materials. Just to compare, the normal atmospheric pressure where you are right now is of about 10 to the 5th pascals. Curiously enough, in most countries, the air pressure that you need to put in the tires of your car is usually indicated in psi, which are those weird imperial units that mean pounds per square inch. Most cars use about 32 to 34 psi to work properly. The linear equation that we have introduced here only applies in the linear regime. But this covers many interesting real situations. May science be with you.